All right, so we are doing our penultimate recitation of the summer. And right now we're looking at recitation, the first recitation of the week is going to be on more stuff involving the divergence theorem. Now, we looked at the divergence theorem this week. The divergence theorem tells us that if you've got a closed surface S, and when we say closed surface, what we mean by that, literally, is a surface that encloses some region E. So think, for example, spheres, think of tetrahedra surfaces, think of, or pyramids. Think of cubes and graphs that are bounded by some graph in some other plane. Lots of different examples of this. So these are so that's what we mean when we say a closed surface. Well, when are we allowed to use this theorem? Well, we can use it if really in two different circumstances. If we're going in the forward direction of this equation, then we can do this whenever we're taking the surface integral of a vector field over a surface that encloses a solid region in R3. Again, think of spheres and cubes, etc. Or you can use it when you're taking the triple integral of the divergence of a vector field. And when I say that, what I mean is when you're taking a triple, you're looking at the right-hand side, you're taking the triple integral of something that you know to be the divergence of a vector field. And note, by the way, that the divergence, of course, it's a dot product of this nabla operator with a vector field. It's a scalar quantity. So it's very important to keep in mind that the divergence is a scalar quantity. Okay, so let's do some examples of this. Let's suppose we want to take the, mostly these, we're going to be going in the forward direction. So if you want to, for example, evaluate the double integral of some vector field, here's the vector field y squared z cubed in the I direction, plus 2yz in the j direction, plus 4z squared in the k direction. S is the positively oriented surface of the solid bounded by the paraboloid z equals x squared plus y squared, and the plane z equals 9. Now, you don't have to be an amazing artist, but you should try to have some idea about what this thing looks like. In this case, we're looking at a surface that looks something like this. You've got your coordinate system. And in this case, we're looking at a surface that's bounded, that's the solid bounded by this paraboloid. This paraboloid that's given by, and it's the usual paraboloid that we're used to, which is z equals x squared plus y squared. And it's bounded by both this paraboloid and the plane z equals 9. So if we want to use the divergence theorem, here's how we're going to go about doing that. So in this case, that's all. The key phrase here is surface of the solid. And when we're saying surface of the solid, well, that's literally what the divergence theorem is all about. It's literally about a surface that's the actual surface of some solid. And here's the solid. Now, you don't need to be a great artist, but you should try to have some idea about what this thing actually looks like. Now, the solid in this case, we can call E, which we use, and E is all x, y, and z, so that we have, and just staring at this thing, we realize that this, this surface, you cast a shadow down onto the xy plane, and it's all of these, it's sitting over the circle of radius 3, right? So it's sitting over the circle of radius 3 in the xy plane. 3 because that's what x squared plus y squared equals when you're all the way at the top of the surface casting the largest shadow possible. So it's all points x, y, z, so that x squared plus y squared is less than or equal to 9, which also makes sense because it's, z is x squared plus y squared and z is bounded above by 9, so it has to be everything less than 9. And meanwhile, z is between x squared plus y squared is less than or equal to z, less than or equal to 9. So now if you want, you can also write this in cylindrical coordinates. Might not be a bad idea. That would be r theta z, so that we have r, our radius, is between 0 and 3, and z is between r squared, and 9. And both those ways are, both of these are perfectly valid expressions for doing this. Now we're going to need to calculate the divergence. So the divergence of our vector field, it's just the derivative of each piece individually, the derivative with respect to x of y squared z cubed plus the derivative with respect to y of 2yz plus the derivative with respect to z of 4z squared. And that's going to come out to y squared z plus 4/3 z cubed. Okay, so now we know what the divergence is and we know what our solid is. So now we can hit this thing with the divergence theorem. ds triple integral over this region E of y squared z plus 4/3 z cubed. That's the divergence of this vector field. Right? No, it's not. Oh boy, I'm starting off strong today. I anti-differentiate instead of differentiate. Usually the mistake is to go in the opposite direction. Oh boy, off to a good start today. Let me try that again. 2z plus 8z. It's going to be much simpler. This, in other words, is 10z. It's going to be a much simpler thing to integrate now. Okay. Oopsie. So this is why we always check our work. This is why we always make sure that we're doing the right thing. Now, probably the best thing to do here is to convert this thing into cylindrical coordinates. So they can go from 0 to 2 pi, r can go from 0 to 3, and z is going to go from r squared to 9 of 10z dz, 10z r dz dr d theta. Anti-differentiate with respect to z. That's going to be the integral from 0 to 2 pi. Integral from 0 to 3 of 5 z squared r dr d theta. But you're evaluating this from z equals r squared to z equals 9. So I get the integral from 0 to pi over 2. Oh, sorry, 0 to 2 pi, excuse me. 0 to 3 of 5 times 81r minus r to the 5th dr d theta. Okay, so going through this is going to become, this is going to get a little bit large, but that's okay. This is going to become the integral from, or you can, right, this is the integral from 0 to 2 pi of, now in this case, we're going to get, what's 5 times 81? 5 times 8 is 4, so it's 405 over 3. R squared. Sorry, 405 r cubed. I meant to, not r squared, r cubed. Sorry. I'm being silly. Minus 5/6 r to the 6th from r equals 0 to r equals 3 d theta. Or in other words, 2. And at this point, you're just going through the motions. It's a little bit of a slightly obnoxious integral, but it's 2 pi times 9/2 times 405 minus, now 27 times, now this becomes r cubed, so, excuse me, 3 to the 6th. 81 times 3 is 243. So that's good enough. This becomes minus 5 halves times 243. And you can clean that up a little bit. This is, and I won't go through the whole thing because it's kind of silly at this point, but it's 9 times 405 minus 5 times 243 times pi. That's about all I really care to do to go through this whole thing. That's our final answer, though. Now, you don't have to use the divergence theorem for this problem. You can do this directly. And if you want to do it do it directly, well, then it comes down to using the formula we had before, which was that you're going to use, oh, sorry, that's silly. You're going to use f dot ds is going to be the double integral over your domain of parameterization of f of r of uv dotted with ru cross rv dA. Now, it wouldn't be that hard to do that in this case because but the only thing you have to be careful of is the orientation, because in this case the orientation of the graph is going to be downward. Now, I'll show you how to do this in the online notes, but I'm not going to do this right now, just for time purposes. But in principle, you can do this either way, either directly or with the divergence theorem. But I think the divergence theorem is a little bit easier in this case because with the divergence theorem, you only have to do one triple integral, but doing it directly, you have to do 2 double integrals. So you're adding an integral, which I think is more trouble than it's worth, in my opinion. So here's another example. What if you want to take the double integral of f dot ds and, wait a second. Okay, I made a mistake there because I forgot to include what the actual surface, what the actual vector field is in that case. So here's your vector field, and S is the surface of this box, and it's enclosed by these planes: x equals 0, x equals a, y equals 0, y equals b, z equals 0, and z equals c. Again, you don't have to be an outstanding artist, but you should make an effort to understand what exactly the situation is that we're dealing with here. And in this case, the situation is, well, we're dealing with a box, right? We're looking at the surface of some kind of a box in 3 dimensions. Here's our surface. And you may think to yourselves, wait a second, that's not a surface, that's obviously a solid. Well, yeah, but we're told that it's the solid is bounded by, we're told that it's the surface of this solid where we've got lengths going from B and C. So that's the surface that we're dealing with. And of course, we want to use the divergence theorem because it's the surface of this box, right? So that box is easy to work with. So our surface E in this case is just all x, y, z. So that x is between 0 and A, y is between 0 and B, and z is between 0 and C. So in this case, we'll calculate the divergence of this thing. The divergence of the vector field is going to be 2xyz in the I direction, plus another 2xyz in the j direction, plus 2xyz, 2xy in the k direction, or in other words, 6xyz. Kind of see where this is going. The double integral, in this case, f dot ds, is 6 times the triple integral over this solid xyz dv, which is a pretty straightforward integral in this case. Just iterated 0 to a, 0 to b, 0 to c, xyz dz dy dx. If you wanted to, you can separate this because this is a separable integral. Integral from 0 to a x dx plus integral from 0 to b y, oh, sorry, not plus, let me try that again. 0 to b y dy, integral 0 to c z dz, if you so wish. So you can write this in this case as 6 times. Now you integrate x from 0 to a. That's going to become 1/2 a squared. Same principle, 1/2 b squared times 1/2 c squared. The whole thing, in other words, is going to become 6/8 a squared b squared c squared, or in other words, 3/4 a squared b squared c squared. That's it. That's pretty much all that this really is going to come down to. It's a pretty simple problem if you use the divergence theorem. Now again, do you have to use the divergence theorem here? No, you can do this directly, but it's a bit of a pain. If you try doing this directly, it's going to be a little bit frustrating because you have to deal with with 6 different surfaces. I suppose in a way you really only have to deal with 3 of them because the vector field is 0 in the XYZ coordinates, in the coordinate planes, but still, it's better to do this with the divergence theorem so you don't have to worry about dealing with 3 different planes or 6 different planes on each side. I think the divergence theorem is the way to go for this particular problem. All right, so sort of in a similar vein, dealing with an arbitrary kind of surface, what we're dealing with in this case. So what if you want to take this double integral over this surface? In this case, your vector field is zi plus yj plus xzk. S is the surface of the tetrahedron, and tetrahedrons are traditionally considered to be solid objects, but in this case, we're talking about the surface of the tetrahedron, so we're only looking at the surface of the thing, and it's enclosed by the coordinate planes and the plane x over a plus y over b, plus, that should be a plus, not an equals. That's a typo that I'll correct in my notes, plus z over c equals 1. A, b, and c are positive numbers. Now, if you think about that for a second, you'll see what that means is that the plane this plane contains the points a0, 0, 0, b0, and 0, 0, c. So what we have in this case, our surface looks something like this. You've got your tetrahedron, but it looks something like this. So here's your tetrahedron sitting inside your coordinate plane, z, x, and y. And here's A, here's B, here's C. So this is what your object looks like in this case. Again, do you have to use the divergence theorem here? No, you can do it directly, but it's not really advisable because you have 4 different surface integrals that you have to deal with, and one of them is slanted, so that might be a little bit frustrating. So let's try doing this without doing this directly. Let's try using the divergence theorem. Now the divergence of this vector field in this case is just 1 plus x. Automatically, that's a much easier integrand to work with than the original surface. What about the region? The region we're integrating over, it's all x, y, and z, so that now x is going to be between 0 and a. What about y? What about that line over there? Well, that line is given when you have z equals 0, so that's x over a plus y over b equals 1. Or in other words, y is equal to negative b over a times x plus b. Right? So in this case, you've got x going from 0 to a, y going from 0 to negative b over a x plus b. and z going from 0 to, and then z is going from 0 to, let's see, this would be c minus c over by minus c over ax. But we're actually not going to use this parameterization per se. We're going to be a little bit more clever than that. So, not c, s. F dot ds, well, that's the triple integral over that region of 1 plus x dv. Or in other words, the triple integral over e of just the constant function 1 plus the triple integral over e of x dv. Now, you can just calculate the volume of the tetrahedron, which isn't really that hard to do. The first volume is going to be 1/3 area of the base times the area times the height, and in other words, 1/3 times 1/2 times the base, which is a times b times the height, which is c, or plus integral from 0 to a, integral from 0 to negative b over a, x minus b, integral 0 to, plus b, integral of negative c over a x minus c over b y plus c x dz dx dy. Dy dx, excuse me. So we've got 1/6 ABC. Now we can actually make our lives a little bit easier by strategically changing. Now, can we make our lives easier by strategically changing the order of integration? Maybe, maybe not. Not super clear. But what we can say is this is going to become the integral 0 to a, integral 0 to b minus b over ax times negative c over ax squared minus c over bxy plus cx dy dx. And now we're dealing with a fairly straightforward double integral, and we've seen this kind of thing before. So what's this going to become? This is going to become this is still 1/6 ABC plus integral from 0 to a of negative c over a x squared times b minus b over a x. I'm going to run out of space, so I'm actually going to pause for a second. Okay. Actually, having looked at this problem for a little bit longer, I'm now seeing that the final answer actually becomes a little bit complicated. So I'm not going to go through that whole thing right now, but it would be reasonable, for example, to try setting up something like this. So maybe when I actually write the notes, we'll just consider about setting it up and then saying, hey, this is what it comes out to. But it's just a computational mess, but the actual setup of this thing is what we really care more about, and you should be able to do. So we'll move on to the final example that I wanted to look at for today. So here you have this triple integral for this vector field. S is the surface of the solid bounded by the cylinder, x squared plus y squared equals 4, and the planes z equals y minus 2 and z equals 0. Again, you should try to have a general gist of what this thing actually looks like. So what we should be thinking of is a plane z equals y minus 2, and it's bounded by this cylinder and that plane. So here we have our our sorry. And some kind of, actually, if it's z equals y minus, no, that is right, that is right. So here's what our solid looks like. I like this tube of lipstick. So, so we want to try to figure out what this thing, what the divergence comes out to. So the divergence in this case, so here's our solid. You should always be able to try to write down what the solid is. In this case, you can talk about it as all x, y, and z, so that x squared plus y squared is less than or equal to 4, and 0 is between z and y minus 2. Or you can write it in cylindrical coordinates as all r theta z, so that theta is between 0 and 2 pi, r is between 0 and 2, and z is between 0 and 0 and r sine theta minus 2. What's the divergence? The divergence of this vector field is going to be y plus 2z plus 2y minus 2z. Or in other words, 3y. If you want to write that in cylindrical coordinates, if you want to write that in cylindrical coordinates, that's just going to come out to 3r sine theta. Okay, so to actually calculate this thing, we're going to have to remember a little bit about how triple integrals work. So this becomes the integral from 0 to 2 pi, integral from 0 to 2, integral from 0 to r sine theta minus 2, 3r squared sine theta dz dr d theta. In other words, this is the integral from 0 to 2 pi, integral from 0 to 2 of 3r cubed sine squared theta minus 6r squared sine theta dr d theta. Now, sine squared of theta, there's sort of a standard way of doing that. The standard way of doing sine squared theta is going to be by using so we can write this as the double integral from 0 to 2 pi, integral from 0 to 2 of 3r cubed times 1/2 1 minus cosine 2 theta dr d theta minus 6 times the integral from 0 to 2 pi, integral from 0 to, actually I'm going to change the order here because I can do that because the bounds are constant, 0 to 2, integral from 0 to 2 pi, r squared sine theta d theta dr. And the reason I did that was because this term will actually vanish. This is going to become, because if you integrate from 0 to, if you integrate sine from 0 to 2 pi, you get cosine, right? You get negative cosine. Negative cosine evaluated from 0 to 2 pi, that's 0. So this whole thing will actually vanish. That whole thing goes away. So what we're left with, and by the way, the same thing is true for cosine of 2 theta. So what we're left with is the integral from 0 to 2 pi, integral from 0 to 2, 3/2 r cubed dr d theta. That's it. That's all that's left over after a whole bunch of stuff, because the cosine 2 theta, that's going to go away too once you integrate that. So that's all that's left over. So this whole thing is going to now become 2 pi times 3/8 r to the 4th from 0 to 2. 2 to the 4th is 16. 2 times 16 is 8. The whole thing is going to become 6 pi. Or not 6 pi, I'm sorry. 2 times 16 is 32, it's 8, so it's 4. So actually, I'm sorry, it's actually 12 pi. My mistake. That's the final answer. And again, yes, you can do this using the direct approach, but I think that the divergence theorem is a lot easier in this case. All right, so that's all that we'll do for today. Hopefully this was helpful in identifying when the divergence theorem is useful and why it's often much more useful than trying to do it directly, especially when you've got something that involves lots of different pieces to it. So the key phrases to look out for is the phrase surface of the solid. Surface of the solid is often something that's a major indicator of, yeah, divergence theorem might be a lot better in this case. All right, thank you everyone, and I will talk to you guys again on Friday. Good luck.